Welcome, everybody. It's a pleasure to be here, and I, first of all, want to thank Pat and for his helping to set up logistics, and Grady and Bob, who's doing the audiovisual. I'm hoping this will be very interactive, and since we're all going to be with us together the next couple of days, I thought it'd be good just to go around the room and introduce yourself, your affiliation, and what experience you have with either visual or imaging or none of the above in terms of astronomy, just so we all get to know each other. So even during the break, if somebody hears somebody's interest, they can hook up with them, network them as well. So why don't we just start here, and let's just go around the room and introduce ourselves. So Dennis?
Dennis Ritz, member of SDAA, and do some variable star photography.
Dennis Blanco, I teach physics and astronomy at Rosemont College. PhD research uses telescopes smaller than 4 meters, but I'm currently working with Pat and Russ and colleagues, getting some of our students doing the double star research. Right now using an iTelescope, but we're going to start folding in our own telescopes and cameras.
Actually, I think I'm going to pass the microphone around so it'll be recorded as well. So if you could just also pass the mic around.
Okay. Yes, Larry Vikander with San Diego Astronomy. I have a C8 telescope and a 20-inch Dob. I've done a lot of observing through the 20-inch and some astrophotography with the 8-inch.
Hi, I'm Jim Bruton. I did some eclipsing binary photometry years ago in college with photoelectric photometers, believe it or not. And I've done a little bit of CCD eclipsing binary photometry for AVSO, which I'm a member of, and also I'm a member of SDAA.
Hi, I'm Reed Estrada, and I've been working with Russ, Janae, and Pat, and some of the other folks that have been here for the past few years, double star astrometry with students. Basically, as an instructor, we've built several large telescopes personally that we've used for that, and then some other projects that Russ has had us work on. So.
Hello, my name is Skylar Larson. I'm not an astronomer. I'm a high school student under Pat and Grady. I'm working to write my own paper on binary star systems.
My name is Bill Ripka. I'm a retired pharmaceutical chemist. My experience here with SDA has been mostly with computational work with the Kepler data, working with Alan Schmidt at Harvard.
My name is Kyle Correa, and I'm a student at Miramar College, and I'm also doing the binary star research.
My name is Hilda Vandenberg, and I got my astronomy and physics degrees at San Diego State a long time ago, so it's been a long time since I've done any astronomy research. And I taught at Miramar. I worked at General Atomics. I've been all over the place. I probably have ADHD or something. But right now I'm doing the double star research under Grady and Pat. So is my daughter with Skylar at Mount Everest Academy. And I'm hoping to bring it to the BWise program, which is better education for women in science and engineering. So hopefully we can get a team together to do that.
Hi, my name is Michael Finney. I teach a postgraduate course in remote sensing at the University of California. Also had some experience developing ISIS, which was a NASA USGS codes for spectrometry exploitation. Worked on Galileo, looking to continue to contribute in this environment. Worked with Grady and Pat with the Army-Navy folks in the past.
Thank you. Rachel?
Hi, I'm Rachel Freed, and I do a lot of astronomy education work. And one of the things I want to mention right now is that I work with the Global Telescope Network, and we're trying to help bring people with telescopes together and with pair them up with students and get more people involved. So if anyone's interested in participating in that, I'd love to talk to you.
I'm Grady Boyce, the other part of the Boyces. I teach the online course and some face-to-face courses. I do course curriculum development for exoplanets and photometry and manage most of the online stuff for Brief.
You've already heard it from me.
My name's Alexander. I'm a student out of Mesa, and I'm also working on the binary project with Pat and Grady, and Cal's my partner over there in this project.
Hi, my name is Sina, and I teach at Mesa College, and hopefully I'll be able to contribute some tonight, too.
Let's see, I'm Scott Dixon with SDAA, and I do quite a bit of narrowband imaging from Poway, where it's really bad skies. And I've also been involved a little bit with the development of the Taro Robotic Observatory.
Hello, I'm Jeannie Anderson. I'm a member of SDAA. Sometimes I run the 22-inch for outreach. I go back to my degree in astronomy in the moldy old 1975 from Maryland, and I just want to update all of my skill sets and knowledge and fascination with exoplanets. I've been to every lecture in town by our wonderful scientists.
My name is Alan Priest. I'm a member of the San Diego Astronomy Association, and I'm currently teaching a high school session of Pat's double star astrometry course.
I'm Jeff Horn. I also have a moldy 1975 degree in astronomy, but from UCLA. But currently I've been doing some CCD photometry for the AAVSO.
My name is Jerry Horn. I also have another moldy astronomy degree from UCLA in 75. But I've been doing a lot of variable star research for the AAVSO and SAS, presenting papers and publishing there, and more recently become an adjunct professor of astronomy at the College of Southern Nevada in Las Vegas.
Hi, Bill Nguyen. No moldy astronomy degrees yet, but I guess I'm going for one. I'm part of the SDAA and the AAVSO. I do cataclysmic variables and some spectroscopy.
Hi, I'm Jerry, member of the SDAA, amateur astronomer.
Go ahead. James Searcy. I'm really a visual observer, so this is really my first thing with photometry at all. But it's part of getting better at the Dosening in Palomar, where they're doing a lot of photometry about exoplanets right now, so having some practical knowledge would be good.
Ken Searcy. My degree in electronic engineering is even moldier than any other degree here. I'm a member of SDAA, and by the way, I'll be organizing the program meeting, so I'm looking for speakers. I'm primarily a visual observer. I'm a docent at Palomar. I spent a lot of time helping one of my friends get his master's degree, so I'm very familiar with imaging on professional astronomical telescopes, but not the data analysis part, which is what I'm really looking for.
Okay, well, thank you all very much. You hear me okay? Up? Okay, well, I think as you heard, we have a wide variety of experiences, both academic and practical. So I think this should be a challenge to try to impart new information. Hopefully we'll try to do that. Let me first start with a question that already has been asked a couple times before we started here, which is, what do we mean by small telescope? I would say at least 8-inch. This has come up probably 3 or 4 times this morning. So 8-inch telescope probably on the small side as far as being able to do exoplanet observing. Pat sort of touched a little bit on the agenda, but let me go through a little bit more detail as far as what I think the objectives are of this workshop. The first is to be able to have you come away with an understanding of high precision photometry, which is fundamental to not only exoplanet observation, but double star and other types of research-oriented observations that you might be interested in doing. So we'll spend some time this morning on that, and then specifically how it will apply to exoplanet observing. We'll go through some of the best practices with exoplanet observing. These best practices have evolved probably over the last few years, more recently with a number of amateur astronomers who have gotten involved in exoplanet observing. They've sort of become a lot more fine-tuned as to what are accepted best practices. We were hoping to actually conduct an observation this evening, which will sort of put in practice some of the best practices. As Pat said, if we're not able to do that, I do have a data set of calibration images, raw images that we can go through tomorrow as if we actually did take that observation this evening. We'll also spend a lot of time tomorrow doing an analysis of that observation. That of course, is sort of the key to getting some real science out of some of these exoplanet transits. We'll review what's involved in publishing a paper. One of the key objectives, I know, of the workshops and seminars that Pat and Russ and Grady have been putting on and Bob have been putting on is to get to the point where folks can actually publish a science research paper. So we'll also go through some best practices as far as that's concerned. We'll discuss some professional amateur collaborations that are currently ongoing, and more importantly, ones that are coming up very soon that are going to actually require even more involvement by amateur astronomers in terms of exoplanet research. And we'll also look to the future as far as some intriguing ways that amateur astronomers can even go a little bit further than what we've been doing up to this point. That is to say, up till now it's been, as we'll spend most of the time talking about, generating light curves. But we'll talk about some intriguing technologies that might allow for direct imaging of exoplanets. And we'll save that for tomorrow. I'd like to make this as interactive as possible, so feel free to raise your hand at any point. I want to make sure that as we're going through this, that folks don't kind of stay behind in terms of where we are, because it all builds upon each other. And furthermore, those of you who have those moldy astronomy degrees, or those of you who have fresh astronomy degrees and want to chime in as far as your thoughts, feel free. Okay? Okay, I sometimes start my exoplanet talks with a surprising answer to this question, which is how many stars have exoplanets going around them? If we look up at the night sky and see all the stars up there, of course, with our naked eye, those are stars just within our Milky Way galaxy. And astronomers now believe that most of them have exoplanets orbiting them. Some of the orbits from our point of view are circular in this fashion, so we can't see them and we can't see any disturbance of the starlight. Some are a little bit more inclined, and some are dead on with our line of sight. And it's these set of exoplanet transits that we will mostly be talking about, because those are the ones that are most observable by amateur astronomers. The others are detected, have been detected by professional astronomers, and in some cases actually by amateurs, and we'll talk about that as well. But for the most part, we'll be talking about planets transiting stars where they are within almost directly our line of sight. And furthermore, we'll be talking about large, what we call hot Jupiters, large planets, Jupiter-sized planets close to their star. So that's sort of the realm of the kind of exoplanet observing we'll spend most of the time talking about You may have all heard of Kepler, which has been sort of the premier space telescope for doing exoplanet discoveries. That now, Kepler is now sort of in its final days of life, but it has been the workhorse for most of the exoplanet transits that have been discovered. And furthermore, even some in the so-called habitable zone, which I'm sure many of you have heard about, which is this zone around a star that is just right for water existing. Now, let me just add my own little editorial to that. I think we've all now know that even in our solar system, we're finding water everywhere, right? We're finding water in the shadows of craters in the moon. We're finding water, you know, hidden under the crust of some of the moons of Jupiter and Saturn. And furthermore, we are rather water-centric because that's how we know life has evolved here. But if you remember the days of Jacques Cousteau, when people have put down those robotic submarines down to the depths of the Pacific and have seen the life coming out of the volcanic eruptions, you know, where life there's no photosynthesis, and it's chemically based sort of life down there. I would just sort of put out there that, you know, water, again, we're very much involved with looking for where water is, but I would argue there may be other types of life. I'm not saying intelligent life, but other types of life that might not be water-based. So the goal, of course, is to find planets, Earth-sized planets, in the habitable zone, because the belief is that's where, if there is life, that's where it's going to be. And in fact, furthermore, we want to know, how do planets form? So the whole area of exoplanet science and research has to do with planet formation. How do planets in other distant distant systems form? Because that would help us answer the question, how do planets in our own solar system form? I had the privilege of speaking at NASA a couple weeks ago to their exoplanet group, and my host, who is one of the main researchers there on exoplanet atmospheres, was telling me over lunch that she gave a talk at a conference on Earth-based atmospheres, because what she was trying to bridge the gap of is understanding exoplanet atmospheres may be applicable to Earth-based atmospheres as far as what's happening here with global warming and that sort of thing. And she was amazed that the scientists who are looking at Earth-based atmospheres had not considered a parallel of looking at exoplanet atmospheres. So there is, beyond just planet formation, even in terms of environmental benefits of understanding how atmospheres on exoplanets form, how they decay, are significant to here on Earth. But the ultimate goal is to detect biomarkers in the atmosphere of distant planets. We're not there yet, but you know, an indication would be that there is some type of life on exoplanets. If, for example, we see, you know, oxygen and methane and other indications in the atmosphere of an exoplanet that might be indicative of some type of life. So getting to look at atmospheres, we'll talk tomorrow about some of the future space telescopes that are potentially going to be able to do that, hopefully in the next probably 5-6 years. Well, when we think of exoplanets, I think many of us just think of like our solar system with, you know, a few planets going around a distant star. That's true, except, again, most of what we're going to talk about and most of what has been discovered, most of the exoplanets, have been these hot Jupiters, as I described earlier. Large Jupiter-sized planets next to their host star. But we also now have discovered that some of these distant systems also have multiple planets. We've now discovered that there are some systems that have 3, 4, or more planets going around them, which is not a surprise, but But we are, as we become more advanced in terms of our technology for detection of more than just hot Jupiters, we are finding that we're able to stretch out further from the host sun a discovery of these planets. You can imagine, though, as one moves away from a host star, the difficulty now of actually detecting those planets. And in some cases, the detection of these planets are done simply, in some cases, just simply based on timing variations of the hot Jupiter. Because of the slight pull of some of those planets, there's a maybe slight timing variation that would cause the innermost planet to have a slightly different time. So the detection of some of these outer planets is still, in many cases, indirectly. We will see, however, an example where there was direct imaging of some of these outer planets. We know that there are some planets that are orbiting multiple stars. There are double and triple star systems where there's 3 stars orbiting each other, and in the midst of all of that, there's an exoplanet. These have been observed. I, in fact, have done my own observations of a double star system where there's an exoplanet going around it, and what you can observe are about 5 different occultations, right? The primary over the secondary, secondary over the primary, planet over the primary, blah, 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 right? So just in some of these multiple star systems, amateur astronomers are doing observations to distinguish whether it's a primary occultation over a secondary or a planet's occultating a secondary and so on. And that's actually now very active. So, yes, question. Pat? Pat's question is, how many of these multiple star systems are there? In fact, I saw just this last week, I can't give you the exact number, obviously, but a large number, much more than we ever thought, of multiple star systems. Right. Yeah. So Pat's question is, how tight is the separation between primary and secondary stars in some of these systems? Let me defer that to, I do have some data on that, but I know that one of the difficulties in distinguishing a drop in the light of a curve is whether it's what's called a nearby eclipsing binary, namely where it's so close that the period of that secondary mimics, and the light curve mimics a planet. And so, you know, some of these planets are 0.05 astronomical units close to their host star, which, you know, as you know, some of the secondaries, some of the binaries are, you know, can be rather close as well. So, yes. So the question was, orbital mechanics would suggest that these are unstable, and is it surprising there's many of them? I guess I just go by the numbers with the billions of galaxies out there and the billions of systems. You know, there's probably millions of, you know, I don't, you know, I think it's, I would say this. My belief is that it's more common than folks had thought, because I would say just in the last year, I think they found maybe even a quadruple system. So it's much more common, I think, folks have realized. So those of you who are doing binary star observations, you know, I think what's relevant here is that you may have a planet going around those binary stars as well. Surprisingly, there are a huge number of planets that are free-floating that got kicked off out of their planetary system and are floating around. And there's thousands of them in the Milky Way galaxy. And it's been, I think, not only suggested, but I think, and I'm not quite sure if it's just through spectroscopy or whatever, that some even have a little atmosphere around them. Now, there's no sun to do, you know, any kind of photosynthesis or anything, but there are free-floating planets that are out there. Yes?
Was Kepler the instrument that found the free-floating?
So the question was Kepler the instrument that found the free-floating? I don't think so, because Kepler focused mostly on transits, which these aren't going to show any transits. So, yes?
So how were these discovered? I'm very curious.
Yes. So the question was, how were these discovered? And the answer was through gravitational lensing, which if you've ever seen the deep sky field view that Hubble has done of distant galaxies, where there's a foreground galaxy that has come in front of a distant galaxy. If you recall Einstein's general relativity theory with light, a mass causing light to bend, that foreground galaxy was causing a background galaxy to actually be lensed and appeared. So with respect to some of these planets, if you imagine a star or a galaxy system moving in front of a planet, now the light of that planet would have to be large enough to at least get lensed and, and shown. Do you want to add to that at all?
Yeah, it's the mass of that planet that counts for bending the light. I would be interested whether this is a target for amateurs, because what happens is the star behind it that's getting the lensing effect brightens briefly and then dims, not too unlike the fluxes, but I don't know if it's within the scope of that.
Yeah. So the question was, is this within the scope of amateur astronomers to be able to detect a free-floating planet going in front of a background star, and that background star getting dimmed or increased? And I don't know the answer to that, but that's something we can maybe find out in the next day or two.
The answer is probably yes, because the micro-lensing follow-up network uses a lot of backyard scale telescopes for amateur astronomers.
Yeah, so Bob's response was the microlensing follow-up network, MicroFun, uses backyard telescopes to do that. I just don't know if the mass of the planet is large enough here. I mean, certainly with a foreground system moving in front of a background star, there'd be a change in light of the background star. I just don't know if the planet would have enough mass to do that. But yes. Yeah. So the point is that timing is an issue, because these things happen once and then they're gone, and you either catch it or you don't. So the other kind of weird thing is that we also know that planets are orbiting. Their orbit is different from the spin axis of the star. And when you think about how planet formation generally would have occurred, where there's this cauldron of matter that is, these protoplanetary disks that then turn into planets. Generally, you would think, just like with our solar system, that planets are going to be having orbits in the same spin direction as the star. But we know that some planets are going in the opposite direction. The speculation is it's because these planets may have been captured by that star system. So, and there are actually fairly straightforward ways of determining the direction that a planet is rotating relative to its star. Maybe we can get into that a little bit later on how that's done. Not by amateur astronomers, but by professionals using something called radio velocity method. And the last thing that's actually relatively recent is discovery of so-called planetesimals that are either asteroids or planets disintegrating around their host star. And what one would see then is, if you can imagine that object sort of breaking up and looking at the light of the star, you would see this strange light curve happening and changing. And we'll in fact see an actual observation. I helped an analysis of a planetesimal of this sort that was discovered last October that shows over a few days this rapidly changing sort of weird light curve that is indicative of this sort of disintegrating asteroid or planet. Yes? I'm sorry, can you speak up?
Yeah, so hot Jupiters are what we like mostly see with the kind of eclipsing observations.
No. Okay. So the question is, as I said earlier, most of what we're going to be talking about are observing the change in light due to hot Jupiters, large planets next to their host star. And the question was, how are we able to see or distinguish this from disintegrating asteroids I just talked about? Well, these are large enough so that they can cause a significant dip in the light curve. And in fact, we'll show an example of that a little bit later. So it is possible for amateur astronomers, I've done it myself on this one with an 11-inch, to be able to detect this change in light curve. Okay, so when did we first discover exoplanets? Some people will say, well, just in 1992, but it was recently discovered. Some folks were looking at some old plates from the Carnegie Observatory, and they found evidence of an exoplanet that actually appeared in that plate. What this was a spectrum, a particular absorption band, I think, on one of the spectrums that was indicative of probably the planet passing in front of the star. And that was just realized this year. So, one could argue when was the first exoplanet detected? Well, one could argue 1917. However, in 1992, this is where the people generally say exoplanet was discovered around a main sequence star, namely a star like our sun. And I'm sorry, this was the pulsar was discovered in 1992. 1995 was when the first exoplanet around a sun-like star was detected. So what we're talking 20 years, in the last 20 years. Most of the discoveries back here were done using something called radial velocity method, which we'll talk about. In 1999, exoplanet was first detected using a robotic telescope by our own Russ Genet. And this is the light curve. I'm sorry, Russ isn't here. This is the light curve that was created back then. You can see a very obvious drop in light due to the planet going in front of that star. So as of a few days ago, this is the latest count. There are over 3,000 confirmed exoplanets. There's another 2,400 unconfirmed exoplanets. Most of these are Kepler targets that still need to be confirmed. And I'm sorry, your name was Bill. And Bill over here is involved, in fact, in looking at Kepler data to try to go from unconfirmed to confirmed. And it's also been confirmed that there's 297 candidates in the habitable zone. Now, keep in mind, we're just beginning, right, to look at exoplanets. So when you extrapolate these numbers just within the small little swatch that Kepler has looked at to our Milky Way galaxy and extend that to the universe, I mean, the number of exoplanets is just truly astronomical. So what's the challenge? Well, this is a direct image at the Keck Observatory of HR 8799. This is the host star. This was done using a chronograph. And these little dots with the letters are the exoplanets around them. Again, this is a direct image. And as you'll see throughout the workshop here, exoplanets are named with the star name with a small letter. So this would be HR 8799b, C, D, and E, and so on. And you can see that some are very close, some are a little bit further away. And you note the description down here. This is half of an arc second, 20 astronomical units. Astronomical unit, of course, being distant from the Earth to the Sun. So this is the challenge, however, is that if you take a look at this distance, and if I did my math right, trying to image that planet would be equivalent to seeing the light reflected off a baseball next to a lighthouse, trying to do that a mile away. So that's the challenge with trying to directly image. You've got this close-in planet with this huge bright object next to it, this big lighthouse, and you're trying, in a very small separation, trying to image the two. So that's the challenge. That's why direct imaging has been sort of the most difficult part, but yet will be the most beneficial, because that's where we can then start understanding things like the atmosphere of exoplanets and so on. Yes?
I remember hearing a presentation probably in the mid-'80s on trying to direct image a planet around another star, and the conclusion was because of this problem in the atmosphere, it had to be a space-based telescope, very large, probably on the back of the moon, and would occur sometime around the mid-21st century is what they predicted.
Right. So the comment was he heard many years ago that the only way that direct imaging could be done is if a space-based telescope out of the Earth's atmosphere would be able to do it. It wouldn't be for, many more years. But indeed, this is a ground-based observatory has been able to do it. Yes, Bill.
The corollary of that is that you really have a better chance looking at the infrared to detect and that you can only really do well outside.
Right. So Bill's point, in fact, this is what this observation was done with, was in the infrared, because really the infrared what is picking up is the heat, if you will, from those planets. So when we say direct imaging, we're not seeing, like those of you who are doing deep sky imaging, we're not seeing, a little round ball. In a sense we are, but what we're seeing is the using infrared camera. And that's, Bill's kind of one step ahead of me in terms of what amateur astronomers might be able to do in terms of direct imaging. So this is the problem. That's why most of the observations, most of the discoveries have been using an indirect method. And that method is the so-called transit method, which is, as you see here in this little graphic, as the exoplanet goes in front of the star, you see a light curve. This is actually a light curve I did with my backyard 11-inch telescope of WASP-12. And so you can see, you can get very distinctive light curves with small telescopes in relatively light polluted skies. Now, while we're on this, let me say a couple of things which we'll go into later. You can imagine as the planet goes around the star, when it hits each of the limbs, you're going to be looking at the starlight through a lot more of the surface of that star, as opposed to when the planet is dead on. Likewise on this side. So there's an effect called limb darkening. There's a limb darkening factor that has to be considered when one is doing these light curves, and we'll talk more about how that's done. So it's not simply just measuring the light of the sun, of the star that the planet's going around it, but it's also consideration for what filter you're using, what's the temperature of the star, that help determine how we compensate for this limb darkening. The other thing to note, that as the planet goes around to this side of its orbit, what one's able to see, not amateur astronomers but professional astronomers, are able to see what's called a secondary eclipse. Namely, as it goes around here, the back of the sun, at this point there's going to be more light coming towards us, right, because it's light from the star reflected off the planet. But then when it goes back of the star, there's going to be another little dip. So actually there's two dips that occur. There's this big dip when the planet goes in front of the star, and there's a little dip when it goes behind. And furthermore, as it goes behind the star, as it's just sort of like on the edge here, using spectroscopy, professional astronomers have been able to detect certain elements in the atmosphere of the planet. So there's a lot of nuance to just even this transit method. Yes, question.
When you're talking about limb darkening, you're talking about the limb darkening of the star.
Yes, limb darkening of the star. I'm sorry. Yes, the question was when I was talking about limb. Yes, limb darkening of the star. Yes.
Our sun's
So the question is, are sunspots a problem? As a matter of fact, they have to be considered and in fact are observable by amateur astronomers, because what would happen, in fact, I have an observation where we think we detected a star spot, because imagine as the planet is going around the star, what happens if it goes in front of a star spot, namely like our sunspot, right? So it's going to go in front of this star spot, and all of a sudden it's going to be as if the planet went away. And what you're going to see is a little characteristic bump in the light curve. Now, the problem, of course, with star spots, just like our sunspots, is that those are rotating with the star itself. So you may see it once, but then it may go away. But indeed, detection of star spots are possible just by looking at little slight changes in the transit curve of the planet. Okay? So this is the main thing we're going to be talking about today and tomorrow. Yes, question?
Is there also a possibility of the star spots being a false positive?
Yeah, is there a question, is the possibility of a star spot giving a false positive? If you think of a star spot as being there, and the only time, and if you're looking at the light of that star, there's not going to be any change in the light of that star until the star rotates out and the star spot goes away. Then you'll see it drop. But you will not see it drop. You'll see it drop and probably maybe never come back again. So I think it's going to be difficult that there be a false positive with a star spot. So I don't think that's I have not heard that's much of an issue. Okay. The second and one of the earliest methods, as I mentioned earlier, is called the radial velocity method. If you remember from your high school physics, two bodies that are orbiting each other or close to each other have mutual gravitational pull. If you take a look at a star and a planet, there in fact is a pull on the planet just as much as there's a gravitational pull from the star to the planet. And so there's a slight wobble in the planet. If you remember some of the images from that New Horizons took as it was going towards Pluto, and you saw that system where Pluto and its moon Charon were sort of in this little dance with each other, much like that. That's the same effect. So by looking at the wobble, one can determine the mass and the existence of a planet. Well, how does one detect a wobble? Well, if you imagine a star from our point of view again coming towards us and then going away, and you think of the old Doppler shift, and you take a look at the spectroscopy of that star, based on the shift in the spectroscopy, blue, red shift, and so on, astronomers are able to determine the radial velocity from our point of view that star is moving. And then based on that, the existence and the mass of that planet can be determined. Not only that, but as that planet is going around the star and that shifting is occurring, depending upon the direction of the planet, if there is a perturbation in the blue shift, let's say the planet's going this way, right? So there's sort of a blue shift towards us and then red shift. If the planet is going in the same direction, there'll be a change in the blue shift before the red shift. If the planet's going in the opposite direction than the star, there'll be a change in the red shift before the blue shift. That's how astronomers are able to determine the rotation direction of a star relative to the planet going around it. So the radial velocity method involves very high precision spectroscopy. There have been a handful of amateur astronomers who have done radial velocity measurements, in some cases using their own custom spectrographs, in other cases using off-the-shelf spectrographs. There's a couple of papers written by amateur astronomers who have used about a $10,000 spectrograph to actually detect to do a radial velocity measurement to detect exoplanet transit. But with the difficulty and expense of doing it, not many amateurs are involved in that. That is a major method, however, that professional astronomers are using. Yes?
Can both methods be combined to confirm one or the other?
Yes. The question is, can both methods be combined? Absolutely. And the reason for that is because one of the difficulties of the transit method is we can determine, as we'll see in a minute, the radius of the star, of the planet, but not get a good feel for the mass of the planet. With the radial velocity method, because the wobble is a function of the mass of the planet, the radial velocity method helps to determine, at least put constraints on what the mass of the planet is. Bill?
But this suffers from well, it has the same limitation as the transit method. You have to be viewing it as relatively as maybe not exactly as because that wouldn't show that particular.
Right. Yes. Yeah. So Bill's point is that it has to be edge on as well, and the answer is yeah. Now the other thing though with the radial velocity method is that if you imagine the edge on is not sort of going completely horizontal, but is tilted, with the radial velocity method, we can actually determine that change in the plane of the orbit as well. But yes, they do complement each other. The other, which we sort of touched on, is microlensing. If, again, we're looking now into the middle of the Milky Way galaxy, not, off on our arm of the Milky Way or up or down or whatever. And the reason we're looking toward the middle of the Milky Way galaxy is because there's going to be a higher probability of a planetary system moving between us and a distant star. Question?
I think I heard you say that from the radial velocity method you can determine the inclination of the plane of the orbit.
Yes.
I don't quite understand how that works.
So the question is, how with the radial velocity method we can determine the inclination of the orbit. There's an effect called the Rossiter-McLaughlin effect that if you're doing a radial velocity curve, as the planet goes in front of the star, there's a characteristic little sort of squiggle that occurs. And based on that, no, during the transit, I mean, what we're talking about here are transits occurring. It's just a question of which way.
I was speaking of the case when there's only radial velocity.
Right, right. And what I'm saying is with only radial velocity method, looking at the curve of the radial velocity, there's a characteristic little hump. Let me just show it real quick here. So as the star is moving from us and to us, there's this curve just based on the movement, right? As the planet moves in front of the star, there's this little effect that occurs.
But if there's no transit, that effect doesn't exist.
Right. I'm assuming there are transits occurring. I'm sorry.
Now I understand.
Yeah, I'm sorry. No, we're assuming.
If there's no transit, then it isn't possible to determine the inclination.
No, there has to be a transit. Yes, I'm sorry. Yes. Okay. All right. So if we're looking into the middle of the Milky Way, and why are we doing that? Because that's going to be a higher probability of a planetary system moving between us and the middle of the Milky Way. So imagine what happens now. We're looking at it as a star, and all of a sudden, a planetary system moves between the observer and that star. So that planetary system, again, a mass that includes both the host star and the planet, is going to cause a microlensing of this star. So what will happen there is the light curve let's say, is the light curve of the star, all of a sudden the background star starts going up like that as the planetary system is occulting it. Then, when the planet moves in front of this star, there'll be another little sort of dip. And this is then when the transit of that planet occurred as that planetary system was moving in front of the background star. So, with the microlensing effect, we can determine that, in fact, there was some object going in front, and this little characteristic dip here would indicate that there was a planet at that point that transited that star. Now, the period going across here is on the order of weeks. So once it happens, it's gone, because that planetary system now is forever gone, right? So there is I think it was Bob or somebody mentioned, a follow-up network called the Microlensing Follow-up Network MicroFund out of Ohio State, where astronomers are notified of potential microlensing starting to happen so that amateur astronomers can now start looking at observing those planetary transits when they happen. Okay? All right, a very recent, like in the last few weeks, indication of another sort of indirect method of detection of transiting planets is stars. I think it's A stars. Some of you folks may know better than me. They're sort of pulsating stars, pulsating from the standpoint of, if you're looking at their spectrum, that when a planet goes in front of it, it's going to cause a change in that pulsation. So this is a relatively new, again, indirect method for detecting exoplanets. And of course, the holy grail of everything, as we said earlier, is being able to directly image. Because once we can now directly image, we can start looking at atmosphere of exoplanets. Okay. Yes.
We're used to the Kepler survey because it takes a reasonably wide, but actually small, swath of sky and checks all of the stars there for transits. And Palomar's done the same thing, uses a 200-inch dwelling on the spot. So transit method is adaptable to like a survey technique rather than exploitation technique. Are there large-scale schemes like this for radial velocity, or is that too hard?
So the question is, surveys that have been done so far, like Kepler, large-scale surveys, have used the transit method for detecting candidates, exoplanet candidates, and the question is, does the same apply for radial velocity? The upcoming one that is going to be, I would say, the most, the one that's going to have the most effect in terms of doing radial velocity surveys is coming up in the next 5 years, and I'll talk about that tomorrow. So the answer is there is an upcoming space telescope that will, in fact, do much more radial velocity surveys than we've done so far, because most of them have been done from ground-based observatories. Okay. So back to the main method that amateur astronomers use, which is the light curve. There are a couple of key characteristics of the light curve. Certainly the duration of the light curve and the depth. And what we can learn from those two measurements, and by the way, what we're talking about here, typically 2, 3, 4 hours as far as the transit going across, and depths that most amateur astronomers can measure, the 10 millimagnitude, sort of, which is like 1% drop in light. Some even lower. I've been able to get down to 0.6%. Sorry, let me get my math right here. 1% drop in light. I've been able to get down to 0.6% drop in light. So the characteristic of this curve obviously is a function of how big the planet is, because the bigger the planet, the bigger the depth, for example. We're able to determine how far it is from its host star, that is to say the size of the orbit. We're able to determine the inclination of the orbit. If it's, for example, what we call a low skimming exoplanet going across the bottom of the star, we're able to distinguish that from one that's more horizontal right across the face of the star. And another question in terms of false positives is it a planet or is it a eclipsing binary? And there are methods for distinguishing between the two, which we'll also talk about. So a lot from the light curve. Again, these are actual data points that I did of observation. And from those data points, one can do modeling, and we're going to talk a lot about that tomorrow, to get a good fit of what this line should be through those data points. And then based on that, one can determine a lot of interesting characteristics about the planet. Okay. So, question? Yes?
Can you go back to that?
Sure.
So in terms of the inclination, what's the metric in the light curve that you're
The period and the duration. What I can do actually is give everybody a reference to a paper that actually goes through the mathematics of how that's derived, how each of these is derived. It's actually more complicated than you think. The one that's the easiest is the first one, which is the radius, because that's just a function of if you know the size of the planet and you've got a duration of light going across it, or the depth of light, then you can figure out the radius. That's an easy one. The other one's a little bit more complicated. Yes?
Probably a simplistic question, but can you note that all of those points are random, or are some of those light readings reproducible in this?
Right. So the question is, are these data points random or are they reproducible? That gets to the question of accuracy of measurements and uncertainty. These were each of those data points represents the relative flux difference between the host star and the planet. There's some uncertainty in that due to systematics of my setup. There's uncertainty due to other factors such as scene conditions. So yes, there's uncertainty, but in terms of random, they're not like totally random. I mean, they're an observation done with some plus or minus.
I'm just curious how, if any of these points were actually real light fluctuations of the star itself, rather than your planet.
Oh no, each of these is a measurement of the light of the star.
And if you did this several times, these points would be randomly distributed along the same
Yeah, they would be. So the question is, if we did this several times, yes, you would see a different scattering of points, but probably the end result would be the same transit model would pop out of it. Okay? Yes?
I guess I can't remember the reason, but why is the bottom of the transit not flat, and what can you tell from the fact that it's...
Good question. So why is the bottom of the transit not flat, and what can you tell about it? One is, the question that came up earlier is, how can you determine the inclination? If you imagine it going across the center of the star, it's going to be probably more like a bucket shape. If you imagine it skimming across the bottom, it's probably going to be more like a shallow, deep shape. So yes, depending upon the curve, actually there's two other points here. There's a point where this inflection occurs. I don't know. Pat, do you have another pointer? I think my pointer's not. Okay, there's a point where an inflection is occurring here, and that sort of describes that bottom part of the curve, and that helps determine the inclination. Yes?
Isn't one of the primary methods for detecting the inclination is comparing the duration of the positive Fourier effect with the actual, the mass
Yeah.
When you look at the transit model.
Right.
Is that why it's kind of, you have to compare one versus the other to match with the lower mass value?
Yeah. So the question was, I think the question was, is the Rossiter-McLaughlin effect of the radial velocity method complementary to the transit method to confirming inclination? I think it was your question. Yes. The answer is yes. Yes. Yeah, that might be a little bit better. Thank you. Somehow my laser is dying here. Whoop, whoop, whoop. Okay. So, all right. So this is the method, obviously, we're going to be spending a lot of time talking about. Now, I mentioned earlier that how do we distinguish between a planet transiting a star versus a binary star system, where there's a nearby star eclipse doing the eclipse. And the answer is that there's different characteristic light curve that will happen, and if one takes that transit observation with different filters, and if the spectral types of the stars are that much different, then one would see a different light curve depth for a V filter versus a R filter, for example. So based on different light curves depths with different filters, one can help distinguish between a eclipsing binary star and a exoplanet. And as I indicated here, the light curve of an eclipsing binary also is much steeper. This, in fact, is an example I took of an eclipsing binary, and you can see sort of the really dramatic drop in the light here of that curve. And this was, in fact, one of those binary systems I mentioned earlier. This is Kepler, and the S indicates this is a occultation of the primary star by the secondary. And as I said, with these systems, there's 4 or 5 different combinations of occultations. So this was an observation of one of the stars occulting the other star. Yes, Grady.
Is there a rough time frame for each of these exposure data points?
Yeah, so the question is there a rough time frame for each of these exposures? And we're going to get a lot more into that, but to answer your question, the answer is it depends on a lot of things. Depends on the brightness of the star, depends on the filter you're using, depends on scene conditions, depends on your camera, depends on the image scale. So all those factors go into what's the right exposure time. We're going to spend, in fact, probably about 10 or 15 minutes just on that question. Yep. Yeah, so the question is, what are these two light curves? So, this is an output of the models that we're going to talk about tomorrow. The blue curve, the blue dots are, think of them as sort of the raw observations. The red dots are taking those observations and compensating for changes in air mass. We call it detrending. So you may or may not on this one see a little sort of change in the sort of angle of the light curve, but that's the difference. It's all the same data, it's just graphed differently and has this transit going through it. The bottom graph, while we're on it, by the way, and we're going to start seeing a lot of these sort of models here. This is the predicted air mass. It's actually the inverse of it. And let me kind of stop there and just remind everybody what air mass is. So as a star is rising through the atmosphere, you're looking through more air mass than when it's straight up. So the air mass values go from, like 1.5 or whatever up to 1 and then start going higher again. What we generally do is we plot the air mass, actually the inverse of it, and then we plot the total counts of the ADU counts of our CCD camera for all of the, well, called comparison stars. I'm kind of jumping ahead a bit here. But this sort of gives an indication of what our transparency conditions were like, because if it follows that air mass pretty well, that says that, you know, it's good seeing, good transparency. If there's a lot of sort of scatter and drops here, that says there's a passing cloud or something like that. So I'm going to explain these graphs a lot more certainly tomorrow as well. But yes? Right. So the question is, when we're looking at eclipsing binaries, do we look at two light curves? It depends on, I'd say generally when we're trying to distinguish it, we just look at one of the transits, but in two different filters at the same time. So what one would see, if you imagine, let's say this was a a V filter and this was a R filter, but they were done at the same time with just alternating filters. Yes?
So I just want to make sure I understand the big picture here. The top graph represents the raw observations, and the bottom two plots represent a modeling of our atmosphere seeing of that raw data as reverse.
Okay. Right. So the question was, what really are these graphs? Let me explain it again very carefully. The top graph is the observation of the drop in light of the star, but it's relative to other comparison stars in the field. Okay, and that's what all of these are. They're all relative measures. These aren't absolute, just looking at the drop in light of the star. It's all relative to other comparison stars. So yes, this is the raw relative flux of the target star. This next curve is taking that data and compensating for the fact that we know there's a change in air mass, and then putting through it a best fit model of what we think a transit should look like. The bottom curve is, the brown stuff here is what the theoretical air mass is predicted to be, and the blue dots are all of the comparison stars together, what they look like across that period. And so, yes, this line, this brown line is a predicted, this red line is predicted, everything else is observational data.
So how many comparison stars were involved?
So the question is, how many comparison stars were involved here? This one, probably about 3 or 4. Yeah. And it depends on many factors, field of view, and we'll talk more about that later. Yes?
A little confused because the comparison stars are going to be pretty close on the sky to your target star, so I'm surprised that they would be that much of an effective air mass, because wouldn't it affect the comparison stars and your target binary equally? So the relative fluxes would take care of that?
Oh, they do. So the question is, you would think the comparison stars are close to the target, and they all should have the same effects of air mass, and the answer is yes. Yeah, so we're not compensating for the difference between the air mass effect on the comparison stars and the target star. We're the effect on just the target star itself. Yeah. Okay. Let me suggest at this point we take a break, 10-minute break. People get coffee, go to the restroom, and then we'll reconvene. Okay? Okay, thank you.